Deep in space, the James Webb Space Telescope may have just found something that could change everything. A distant planet, more than 100 light-years away, is showing signs that suggest there may be a 99.7% chance of life. If that signal is real, this could be one of the most important discoveries in human history. Before we begin, please take a moment to like, subscribe, and share this video if topics like cosmic mysteries and science discoveries fascinate you. And as always, thank you so much for being here and for supporting the channel. Also, feel free to leave a comment and let us know what time it is where you are and where in the world you're listening from. It is always amazing to see this journey shared across so many different places. Now, let's begin the video. In the cold arithmetic of astronomy, discoveries usually begin as a slight deviation, a narrow bend in a line, a dimming too small for instinct to trust. This one begins the same way. It does not arrive as a blazing image of an alien sea or a dramatic portrait of a distant horizon. It arrives as a sequence of measurements, faint slices of infrared light collected far beyond Earth, where the James Webb Space Telescope drifts in the deep dark near the balance point known as Lagrange 2. There, shielded from the glare and warmth of the sun, its instruments remain cold enough to sense traces of heat and chemistry from worlds that no human eye will ever see directly. Among those worlds is a planet circling a red dwarf star in the constellation Leo, a world catalogued as K218b, lying about 120 light-years from Earth. Its light begins the journey toward human detection before modern flight, before radio, before the shape of the atom is fully understood. By the time it reaches the mirror of the telescope, it carries the memory of a world already more than a century in the past. That world does not look promising at first in the old sense. It is not Earth-sized. It is not clearly rocky. It does not orbit a star like the Sun. It belongs to a class of planets that once unsettles the search for life because they fit nowhere familiar. It is larger than Earth, more massive, wrapped in a thick atmosphere rich in hydrogen, perhaps closer to a small Neptune than a second home. For years, such planets sit in a category of uncertainty, too large to be reassuring, too strange to dismiss. Then the telescope begins reading the chemistry of its sky, and uncertainty changes shape. The method is simple to describe and maddening to achieve. When the planet passes in front of its star, a tiny fraction of starlight filters through the rim of its atmosphere before moving onward through space. Molecules in that atmosphere absorb certain wavelengths and allow others to pass, leaving dark notches in the spectrum. Those notches act like a fingerprint. Water leaves one pattern. Methane leaves another. Carbon dioxide leaves another. If the telescope is precise enough, patient enough, and quiet enough, the atmosphere can be reconstructed from almost nothing. It is a science of absences. Each missing piece of light reveals what stands in the way. What appears first is not the great mystery, but the setting in which the mystery becomes possible. Water vapor seems present. Methane appears. Carbon dioxide appears as well. That alone is enough to make the planet difficult to ignore. These are not proof of life, not even close, but they suggest an atmosphere with complexity, motion, and structure. They suggest a world that is not chemically dead. They suggest temperature and pressure conditions that deserve more attention. Already the picture begins to drift away from the old expectation that life must wait only on a small rocky planet under a familiar yellow star. Already the planet begins to ask for a broader imagination. Then the deeper anomaly emerges from the data. It does not announce itself loudly. It sits inside the spectrum like a detail almost too improbable to touch. The signature appears where dimethyl sulfide should be. On Earth, dimethyl sulfide is associated overwhelmingly with life, especially marine life. It is produced by living organisms and released into the air above oceans, where it becomes part of the subtle chemistry of clouds and climate. It is not one of the usual gases that can be explained away with ease. Oxygen can be made without biology under some conditions. Methane can rise from geology. Even water says little by itself. But dimethyl sulfide belongs to a rarer category, the kind of molecule that makes researchers pause longer than they mean to. At first, caution governs everything. A signal is not a fact. A pattern is not a conclusion. Instruments have noise. Data reduction can introduce false shapes. Unknown chemistry can impersonate the familiar. Astronomers learn early that the universe is full of things that look like revelation until the next observation erases them. Yet this signal does not vanish. It remains after the first pass through the data. It remains when different models are applied. It remains when contamination is considered. It remains when the team returns to the spectrum and asks whether the feature belongs to the star, to the telescope, to the processing itself, or to nothing at all. The line remains where it should not be. This is where the story turns from detection to tension. The planet is not merely habitable in some abstract way. It seems, at least from the first atmospheric reading, to occupy a regime in which life is not absurd. Estimates place its atmospheric conditions in a range that could allow a warm ocean world beneath the hydrogen sky. Some models suggest temperatures around 120 degrees Fahrenheit, not mild by human standards, yet still within a range where liquid water can persist and chemistry can move quickly. In that warmth, under that pressure, across a planet likely covered by deep waters, the possibility of biology begins to stop sounding ornamental. It begins to sound structural, as if the atmosphere may be telling the truth about the surface below. Still, the truth refuses to sit still. K218b is likely tidally locked, with one face turned always toward its star and the other in permanent darkness. Around many red dwarfs, that would seem hostile. A world with an eternal day and an eternal night appears unstable at first glance, divided between burning light and frozen shadow. But a thick atmosphere changes the logic. Hydrogen, light as it is, can move heat efficiently. Instead of allowing the day side to overheat and the night side to collapse into ice, the atmosphere may redistribute warmth across the globe. The same feature that once makes the planet seem alien may be the feature that keeps it livable. The more the planet is examined, the more it resists easy sorting into safe and unsafe, dead and alive, possible and impossible. That resistance gives the signal its power. The dimethyl sulfide feature does not float in isolation. It appears in an atmosphere already rich with ingredients that imply activity. It appears on a world that may maintain liquid water beneath persistent cloud and pressure. It appears around a star dim enough to require the planet to orbit close, but stable enough, perhaps, to provide long spans of time for chemistry to deepen into biology. Nothing alone is decisive. Together, the details begin to lean. Then comes the number that changes the mood of the search. The confidence attached to the detection rises to about 99.7%. In other fields, that might sound final. In astronomy, it sounds dangerous. It is high enough to provoke headlines, but not high enough to dissolve doubt. It places the result in the narrow band where the imagination surges ahead of certainty and refuses to wait. It suggests that the signal is unlikely to be a random fluctuation. It suggests that the feature is real. Yet what real means remains unsettled. Real could still mean chemistry not yet understood. Real could still mean a world stranger than present models allow. Real could still mean life. The distance deepens the unease rather than softening it. 120 light-years is close enough for detailed atmospheric study, yet far enough to make the discovery feel almost theatrical in its timing. Whatever produces that possible trace in the atmosphere does so when Earth still lives in an earlier age. Whatever stirs beneath those clouds, if anything does, has been shaping its world while human beings pass through war, invention, silence, and the first fragile steps into space. By the time the signal reaches the telescope, it is no longer a present event but a historical one, an old breath arriving fresh. So the anomaly settles into scientific memory in the quietest way possible, as a pattern in filtered starlight, as a molecule where a molecule should not easily be, as the first hint that a planet once treated as an oddity may instead be a threshold. Nothing visible moves, no ocean breaks, no organism rises into view. There is only the spectrum, the patient machine, the hydrogen world in Leo, and a question that seems at first almost too large for the data that carries it. If dimethyl sulfide is truly there, then something on that distant planet may already be altering an entire atmosphere. And if an atmosphere can be altered from 120 light-years away, then the universe may have become more crowded long before anyone on Earth learns how to read the signs. The deeper the planet is examined, the less it resembles the kind of world once imagined as the only refuge for life. For generations, the search is guided by a simple instinct. Find a small rocky planet, place it around a stable star, keep liquid water near the surface. Hope that the chemistry of Earth is not a local accident but a repeating pattern. K218b begins by violating almost every part of that picture. It is too large to feel comfortable. It carries too much atmosphere. It circles a red dwarf instead of a sun-like star. It likely does not offer a familiar coastline beneath a blue sky. Yet each of these disqualifications begins, under closer scrutiny, to turn into something stranger. They do not remove the possibility of life. They reshape it. The planet is thought to be about 8 times as massive as Earth, with a radius several times larger. That places it in the blurred territory between a scaled-up rocky world and a scaled-down gas-rich one. In the early years of exoplanet science, worlds in this range seem frustrating because they do not exist in the solar system as direct examples. Earth is small and rocky. Neptune is much larger and wrapped in volatile gases. Between those two familiar types lies a population of planets that once feels almost theoretical, a class with no clear analogue near home. K218b belongs to that awkward middle ground. It is not easy to picture, and because it is not easy to picture, it is easy to mistrust. At first, scientists often suspect that such planets are mini-Neptunes, worlds with deep envelopes of hydrogen and helium above layers of fluid and ice so extreme that life as known on Earth would have nowhere to stand. But over time, new models open another possibility. Some of these planets may be ocean worlds with hydrogen-rich atmospheres above vast layers of liquid water. The term sometimes used for this category suggests a fusion of hydrogen and ocean, an attempt to name a place that is neither truly terrestrial nor fully gaseous. K218b becomes one of the leading examples. It may not have continents, it may not have a solid surface in the ordinary sense, yet it may possess what life needs most, not stable ground, but stable chemistry. That possibility changes the emotional geometry of the planet. Its mass no longer feels only oppressive. Greater mass means stronger gravity, and stronger gravity can preserve an atmosphere for enormous spans of time. Mars, smaller and weaker, loses much of its air long ago. Earth retains enough to remain fertile, though even Earth leaks slowly to space. K218b may hold its atmosphere with far greater determination. The same gravity that would burden any hypothetical human visitor could be one reason the planet remains chemically active across vast eras. A deep atmosphere is not only a barrier, it is a memory. It keeps gases from escaping too quickly. It stabilizes pressure. It widens the range of temperatures at which liquid water can persist. A world once dismissed as too heavy may, for that reason alone, be unusually durable. Its star complicates the picture further. Red dwarfs are smaller and cooler than the Sun, and because they emit less light, the region where liquid water might exist lies much closer in. K218b orbits near its star, completing a year in just a few dozen Earth days. Such closeness introduces one of the more unsettling features of the system. The planet is likely tidally locked. One hemisphere continually faces the star. The other faces permanent night. In an older imagination, such a world appears split beyond repair, one side scorched, one side frozen, with a narrow strip of twilight perhaps offering the only compromise. But that older imagination belongs to thinner atmospheres and more familiar planets. A hydrogen-rich envelope changes everything. Hydrogen is exceptionally good at moving heat. If the atmosphere is thick enough, it can transport warmth from the lit hemisphere into darkness and prevent the great collapse into two hostile worlds. Day and night remain, but the climate may not fracture with them. That is one reason the estimated temperature matters. A world with an atmosphere dominated by hydrogen can remain warm in ways that seem counterintuitive at first. Hydrogen is not a greenhouse gas in the same ordinary sense as carbon dioxide, yet in large enough quantities under sufficient pressure, it helps trap outgoing heat and smooth the planet's climate. Models of K218b suggest a warm regime, perhaps near 120 degrees Fahrenheit in some scenarios, though much remains uncertain because no one has touched the air or sampled the sea. Still, warm does not mean lifeless. On Earth, some of the hardiest organisms thrive in hot water, in deep vents, in acidic pools, in hidden places where biology does not merely endure but adapts with quiet efficiency. What matters is not whether the world feels comfortable to human skin. What matters is whether molecules can meet, combine, persist, and repeat. The unsettling detail is that K218b may offer those conditions on a planetary scale. Water vapor in the atmosphere points toward a reservoir of water below or within the atmospheric structure. Methane and carbon dioxide indicate a chemistry that is not inert. The absence or weakness of some expected gases can be just as telling as the presence of others, because atmospheres are ruled by balance. If a world is left alone long enough, chemistry tends to settle. Reactive compounds disappear or dominate according to the pressures and temperatures available. But on worlds where energy continues to circulate through air, water, and rock, equilibrium becomes harder to reach. Something keeps the atmosphere from becoming simple. Something keeps pushing it away from rest. This is where the planet's physical nature and the mystery of its atmosphere begin to merge. If K218b is truly an ocean world, then the visible atmosphere is only the outermost skin of a far deeper system. Beneath the hydrogen-rich sky may lie clouds, then more dense gases, then layers of warm water extending downward far beyond the scale of Earth's seas. The pressure below could become immense, enough in some models to create exotic phases of water unfamiliar to ordinary experience, with warm liquid above and compressed forms below. Whether such layers would help life or isolate it remains unclear. Some planetary scientists wonder whether too much water can be as limiting as too little, because without cycles that exchange material between sea, atmosphere, and interior rock, chemistry may become trapped. Others point out that unfamiliar worlds may develop unfamiliar forms of cycling, tides, convection, dissolved gases, and internal heat may create pathways not yet recognized. The planet remains difficult precisely because it is too large, too deep, and too unlike home to judge by intuition alone. That uncertainty gives the world its peculiar power over the imagination. A small rocky planet invites comparison with Earth almost automatically. K218b refuses such comparison. It demands a slower form of thought. It suggests that life, if present, may not live on land at all. It may inhabit a warm ocean under immense sky pressure. It may float in upper layers where temperature and chemistry align. It may belong to a biosphere spread not across continents and forests, but through water columns, cloud decks, and atmospheric exchange. The planet is not merely a place where life might have adapted. It may be a place where the very definition of a living environment becomes less anchored to ground. Even the old distinction between habitable and uninhabitable begins to lose its edges here. K218b is not a second Earth hidden in the dark. It is something far more difficult, perhaps far more common, and possibly far older in biological terms than earlier searchers are prepared to consider. If the signs in its atmosphere are real, then life does not wait politely for familiar conditions. It works with pressure, with hydrogen, with deep oceans, with red starlight, with climates spread across eternal day and endless night. It uses what exists. It alters what it can. It changes the sky above it until a distant telescope notices, and that is the central unease of the planet. The more alien it becomes, the less safely it can be ignored. What once makes it an unlikely target now makes it a more dangerous one for old assumptions. If a world like this can hold water, retain warmth, sustain complex chemistry, and perhaps accumulate a biosignature visible across interstellar space, then the quiet category in which it once rests is no longer quiet at all. It begins to widen. It begins to include more planets, more stars, more hidden oceans. K218b stops being an exception and starts to look like an invitation to search where astronomy once barely bothered to look. What the telescope truly sees is not the planet itself, but a subtraction. The star shines. The planet passes across it. The atmosphere around the planet steals a little of that light. Everything that follows depends on understanding that theft, for all the language of discovery, for all the images later attached to the idea of an ocean world in the constellation Leo, the essential act remains almost austere. A machine built by NASA, ESA, and their partners waits in darkness and measures what fails to arrive. From those missing traces, an atmosphere is sketched. From that atmosphere, a world begins to emerge. From that world, a deeper unease takes shape, because the more complete the chemical portrait becomes, the less accidental it appears. The science of transmission spectra, once reduced to plain language, has a severe kind of beauty. Every gas has a habit of interacting with light in its own way. Molecules bend, stretch, and rotate, and as they do, they absorb specific wavelengths with exquisite selectivity. Water takes one set, methane takes another. Carbon dioxide leaves its own arrangement of marks. A telescope sensitive enough to infrared light can record these patterns when a planet crosses its star. It does not see clouds rolling or waves moving below. It sees a code. If the code is clean enough, it can be translated into chemistry. The James Webb Space Telescope is built for this kind of reading. Its mirror gathers faint light with a collecting area large enough to matter across enormous distances. Its sun shield keeps heat from the sun, earth, and moon from flooding the instruments with interference. Its spectrographs divide incoming light into narrow bands fine enough to expose molecular structure in what would otherwise look like a smooth signal. It is less like a camera than a patient listener, tuned to tiny changes in a star's brightness at wavelengths human senses can never feel directly. With exoplanets, especially those around smaller stars, that sensitivity turns the edge of an atmosphere into a readable boundary between ignorance and inference. Yet inference is never simple. The light reaching the telescope has already passed through too many filters to trust immediately. It has crossed interstellar space. It carries the imprint of the star, which must be understood separately from the planet. It passes through an instrument with its own quirks, warm pixels, drifting baselines, minute systematics that can imitate structure where none exists. The atmosphere of the planet itself may contain clouds or hazes that flatten important features and hide others. Then the data must be cleaned, modelled, compared, and cleaned again. Every strong claim is built on a chain of restraint. That is why the signal from K218b feels so strange to those who study it. It survives a process designed to remove illusion. At first, the emerging spectrum seems to tell a comprehensible story. Water vapour appears to be present. That matters because water in an atmosphere, especially around a warm planet in a habitable region, hints at a larger reservoir below or within the system. Methane appears as well. Carbon dioxide enters the picture too. None of these gases by themselves is extraordinary. They belong to ordinary planetary chemistry under many circumstances. They can be produced without life. They can endure for long periods if conditions allow. And yet the combination begins to matter more than any one ingredient: water, methane, carbon dioxide. And a broad hydrogen atmosphere do not simply identify a planet. They define an active environment, a place where radiation, pressure, and chemistry are constantly interacting. The first mystery grows from that interaction. In a quiet atmosphere left to itself, chemical tension tends to relax, molecules react, energy disperses, stable mixtures dominate. But the spectrum of K218b hints at something more dynamic, as though the atmosphere is not merely sitting over the planet but being renewed, altered, and pushed out of simplicity. Hydrogen provides a vast background, a light gas forming most of the envelope. Water suggests exchange with deeper reservoirs. Methane and carbon dioxide appear together in ways that are suggestive, though not yet decisive. The world begins to resemble a system rather than a shell. Even that is enough to widen the interpretive space. If the atmosphere is truly hydrogen-rich, then the old assumptions tied to Earth-like air begin to fail. Life on Earth is so bound to oxygen in the modern imagination that a hydrogen sky seems immediately wrong, almost hostile by definition. But that reaction is provincial. Earth itself has not always been an oxygen world. For much of its early history, life persists in environments with little or no free oxygen, drawing energy instead from other chemical differences, in deep sediments, in hydrothermal systems, in buried microbial realms. Biology learns to use what is available. A hydrogen atmosphere may look alien to human lungs, but that says little about whether it could support other metabolisms. Once that door opens, the spectrum stops being merely descriptive. It becomes provocative. Clouds complicate the reading further. A planet like K218b may be wrapped not only in gas but in layers of haze or cloud that conceal deeper levels of the atmosphere. Such layers can mute spectral features and make the atmosphere appear flatter than it is. Sometimes a weak signal is weak because the gas is scarce. Sometimes it is weak because clouds stand in the way. This ambiguity turns every retrieval into a contest between competing models. A muted feature might indicate less methane, or more haze, or a different thermal profile, or a larger atmospheric scale height than expected. The solution is never drawn from one line alone, but from the way many features fit together. In the case of K218b, the fit remains troublingly coherent. Multiple molecules seem to belong. The atmosphere resists being simplified into noise. Then the anomaly presses back into view, against the broader chemical setting. The possible presence of dimethyl sulfide begins to feel less like an isolated curiosity, and more like an intrusion from another category of explanation. On Earth, dimethyl sulfide is not merely a molecule in the air. It belongs to the metabolism of living systems, especially microscopic life in the oceans. It rises from marine biology into the atmosphere, where it can influence cloud formation and climate. It is entangled with the activity of life at scale. So when a faint absorption feature appears in a region where dimethyl sulfide could plausibly be responsible, the atmosphere of K218b suddenly changes character. It is no longer only wet, warm, and chemically active. It may be biologically disturbed. That remains a dangerous thought, and researchers know it. The history of astronomy is filled with premature certainty. Channels on Mars become optical illusion. Signals become interference. Promising atmospheric features become calibration errors or unexpected abiotic chemistry. That history is why the spectrum of K218b is approached with such caution. The known facts come first. The telescope detects atmospheric components consistent with hydrogen, methane, carbon dioxide, and water vapor. The planet lies in a region around its star where temperatures might allow liquid water. It may be an ocean world beneath a hydrogen-rich sky. A feature compatible with dimethyl sulfide appears in the spectrum. These are the observations. Everything else begins as interpretation. Yet interpretation is precisely where the mystery deepens, because once the known facts are placed together, they begin to suggest a world in chemical disequilibrium. That phrase sounds technical, but its meaning is simple. The atmosphere may contain compounds that should not comfortably coexist unless something is constantly replenishing them. On Earth, life performs that work. Oxygen persists because living organisms keep making it. Methane persists in part because living systems keep feeding it into the air faster than chemistry can erase it. A living planet rarely sits in equilibrium. It behaves like a system with an internal restlessness. K218b begins, faintly and without closure, to resemble that kind of system. The most unsettling part is that this impression does not come from a direct image or a dramatic data spike. It comes from consistency. The spectrum is not loud, it is composed. It keeps returning to the same answer space: water, methane, carbon dioxide, hydrogen, then the possibility of dimethyl sulfide. Each feature alone can be debated. Together they form a setting in which the last feature becomes harder to dismiss. It is as though the atmosphere is not revealing a single surprise, but building the conditions under which the surprise begins to make sense. There is also the matter of scale. To affect a planetary atmosphere in a detectable way across 120 light-years, whatever process is involved cannot be trivial. If dimethyl sulfide is truly present in meaningful abundance, it implies not a hidden patch of chemistry, but a world-sized source or a mechanism not yet understood. On Earth, atmospheric signatures visible from afar arise when local processes aggregate into something planetary. Oceans breathe into the sky. Forests alter gases over continents. Microbes in unimaginable numbers reshape chemistry from below. The spectrum from K218b hints at the same possibility, that the line between atmosphere and biosphere may not be a line at all, but an exchange. Even the uncertainties have a pattern of their own. If the feature is not dimethyl sulfide, then some other molecule with similar spectral behavior must be responsible, and that too would be instructive. It would mean the atmosphere hosts chemistry more exotic than expected under current models. If the atmosphere is more complex than present retrievals suggest, then the world is stranger in one direction. If the tentative biosignature survives future observations, it becomes stranger in another. Either way, the spectrum refuses to lead back toward banality. It does not offer a quick mistake that closes the case and returns the planet to ordinariness. It offers branching mysteries, each anchored to the same narrow bands of missing light. So the telescope keeps reading, and the atmosphere keeps speaking in absences. No ocean is seen, no organism is named, nothing living rises into view, but the code in the filtered starlight grows more coherent, not less. the planet becomes increasingly defined by what its atmosphere removes from the star behind it. And in that removal, in those missing wavelengths, a difficult idea continues to form with unnerving calm. A distant sky may be carrying the metabolic trace of something below it. Not proof, not yet, but enough to make the act of reading an atmosphere feel less like chemical bookkeeping and more like the first attempt to decipher a world that may already be alive. Among all the gases that have been proposed, disputed, retrieved, and reanalyzed in the atmosphere of K218b, one family of molecules changes the emotional temperature of the entire story. Water vapor can be explained in many ways. Methane can arise from life, but also from geology. Carbon dioxide belongs to ordinary planetary chemistry. Even the idea of a hydrogen-rich atmosphere above a deep ocean, while unusual, still belongs to the broad natural diversity of planets. But dimethyl sulfide occupies a narrower space. It does not merely add one more chemical line to the spectrum. It introduces a more difficult category of explanation, because on Earth, this molecule is tied with unusual intimacy to biology. That is why the possible detection does not feel like an incremental step. It feels like a pressure point. Dimethyl sulfide is a sulfur-bearing compound best known on Earth as a product of living organisms, especially marine microbes and phytoplankton. It rises from the ocean into the atmosphere and becomes part of a cycle that links microscopic life to clouds, weather, and climate. It is one of those substances that begins in small bodies and ends up touching the sky. In human terms, it is obscure. In planetary terms, it is strangely revealing, because it belongs to a chain of activity that is difficult to separate from life itself. When a telescope seems to find the spectral hint of such a molecule on a distant world. The question changes from whether the atmosphere is active to whether something living may be participating in that activity. The caution begins immediately and properly. No serious observer of exoplanets forgets how easy it is to move too fast from signal to story. The possible detection in K218b is not a direct sample from air trapped in a chamber. It is an inference drawn from light that has passed through an atmosphere, entered a telescope, crossed detectors, and been reconstructed through models. Moreover, the spectral region involved can be difficult. Molecules with somewhat similar behavior can overlap. Some analyses speak not only of dimethyl sulfide, but also of the related molecule dimethyl disulfide, because the available data may not always separate them cleanly. That ambiguity matters. It reminds everyone involved that the atmosphere is not yet a solved puzzle. The signal may point toward one molecule, or a family of possibilities, or a chemical context not fully anticipated in current models. Even so, the reason the signal creates such disturbance is that the ordinary fallback explanations remain unsatisfying. On Earth, dimethyl sulfide is overwhelmingly biological. That fact alone does not prove that any other world must produce it the same way. Nature often repeats structures through different routes under different pressures and temperatures. A molecule familiar to biology here might arise abiotically elsewhere if enough energy, the right solvents, and the right atmospheric conditions coincide. That is the conservative position, and it is a necessary one. But conservative does not mean comfortable. In the case of K218b, researchers do not have a well-established non-biological factory ready to account for large amounts of dimethyl sulfide in a hydrogen-rich atmosphere under temperate conditions. The signal therefore does not settle anything, but it refuses to settle down. This is the point at which the molecule stops being a line in a spectrum and becomes an argument about worlds. If dimethyl sulfide or a closely related sulfur compound is genuinely present, then the atmosphere of K218b may be doing something that current planetary chemistry does not easily predict. One option is biology. Another is an unknown abiotic pathway. Both possibilities are unsettling. Biology would mean life has already announced itself indirectly across interstellar distance. Unknown chemistry would mean the planet is stranger than present models allow, and that the apparent closeness to biology arises because Earth's own chemistry is only one local example within a larger cosmic repertoire. In either case, the atmosphere refuses to be ordinary. Part of the tension comes from the scale implied by the signal. A molecule visible in a planet's spectrum from more than 100 light-years away cannot come from a trivial process confined to a few rare pockets. The atmosphere of an exoplanet is a blunt instrument. It reveals broad tendencies, world-scale patterns, average signals spread over a disk unresolved even by the most powerful space telescope now in operation. If a sulfur-bearing biosignature candidate is emerging from that averaged view, then whatever creates it must be operating with persistence and reach. It suggests an atmosphere in exchange with a deeper system. It suggests replenishment. It suggests flux. If the source is biological, then the biosphere is not hiding in a cave or a narrow vent. It is participating in the chemistry of the whole planet. On Earth, that kind of participation often comes from life too small to see and too abundant to imagine. The atmosphere of Earth is not only shaped by forests, reefs, or visible organisms. Much of its deeper chemistry is mediated by microbial life, by populations so vast that their collective activity becomes geological in effect. They alter gases, oceans, and minerals over time spans long enough to change a world. That is one reason dimethyl sulfide feels so provocative. It does not point, even in imagination, toward large visible creatures moving through alien seas. It points toward metabolisms, cycles, and planetary influence. It points towards small living systems operating in such numbers that they spill into the sky. That possibility fits uneasily well with the proposed nature of K218b. If the planet is indeed a warm ocean world beneath a hydrogen-rich atmosphere, then a marine biosphere is not a wild decorative guess, but a structurally relevant one. A deep global ocean, stable temperatures, dissolved gases, constant energy from the host star, and a thick atmosphere capable of retaining heat all create a setting in which chemistry could remain active for immense periods. In such an environment, the most consequential life might not resemble anything dramatic. It might consist of floating microbial communities, layered ecosystems in upper waters, or atmospheric interface life feeding on chemical gradients between sea and sky. The likely biosphere of such a world, if it exists, would not need to be spectacular in form. It would only need to be persistent enough to reshape the air. Yet this very plausibility is what forces restraint. A story that fits too neatly is dangerous. Exoplanet history warns against the seduction of coherence. Once a world is imagined as an ocean planet around a quiet red dwarf, rich in methane, water vapor, and perhaps dimethyl sulfide. The mind wants to complete the painting, but the data never fully permit that final brushstroke. Clouds may mask the deeper atmosphere. The temperature profile remains uncertain. The exact pressure at various levels is model-dependent. The ocean itself, though plausible, is inferred rather than seen. Even the absence of ammonia, which some have taken as a clue consistent with a water-rich world, is not a verdict but part of a larger retrieval problem. The atmosphere is suggestive, not transparent. The temptation is to imagine a complete ecology when the telescope has revealed only the chemical edges of one. Still, there is a reason the idea persists, and why the claim acquires so much force in public language. Dimethyl sulfide sits very near the line between chemistry and biography. It is the kind of molecule that makes a distant planet feel less like an object and more like a place with internal processes that may include metabolism. For years, the search for life beyond Earth often depends on broad markers such as water, rocky surfaces, or orbital location. Those are environmental conditions. Dimethyl sulfide belongs to a different category. It is not merely a sign that life could exist. It is a sign that something lifelike may already be at work. Even a tentative glimpse of that possibility shifts the entire search from habitability to activity. This shift also alters how uncertainty itself feels. Before such a signal appears, uncertainty is mostly emptiness. The atmosphere could contain many things, perhaps nothing remarkable. Afterward, uncertainty becomes crowded. If the spectral feature holds up, then some process on K218b must explain it. If future data weaken the case for dimethyl sulfide specifically, the atmosphere may still preserve a mystery in another form, because the sulfur chemistry of the planet will have to be reconsidered. If the feature strengthens and becomes more cleanly separated from alternatives, then the world crosses a different threshold and begins to enter the long, careful territory of biosignature confirmation. In none of these branches does the planet return to being simple. The timing of the claim intensifies that feeling. The James Webb Space Telescope is still early in its scientific life by the standards of great observatories. It has only recently begun opening this level of atmospheric access to temperate worlds. K218b therefore appears not at the end of a mature search, but near the beginning of a more capable era. That means the dimethyl sulfide question is not an isolated puzzle awaiting one answer. It is a test case. It is one of the first moments in which the astronomical community is forced to confront what a real, plausible, but uncertain biosignature might actually feel like in practice. Not a clean triumph, not a cinematic revelation. Something more difficult, something statistical, spectral, revisable, and yet impossible to ignore. And that may be the deepest reason the molecule exerts such pressure on the narrative. It makes the planet feel inhabited even before that word can be justified. Not inhabited in the sense of certainty, but inhabited in the imagination of science itself, where a world begins to acquire internal agency because its atmosphere no longer looks passively geochemical. A sky containing a possible biological sulfur signature is no longer just a sky. It becomes a skin in contact with whatever lies below. It becomes evidence of exchange. It becomes a surface on which life, chemistry, and climate may be writing over one another in slow planetary script. So the molecule remains there, unresolved and persistent, like a stain in the data that grows more significant the longer it refuses to disappear. It is not yet the end of the argument. It may not even be the correct molecule in the final accounting, but it has already done something irreversible. It has altered the kind of question K218b now asks. The world is no longer being measured only for compatibility with life. It is being watched for signs that life, or something disturbingly close to it, may already be changing the air. Science rarely fears a mystery as much as it fears a pattern that is almost convincing. A weak signal can be ignored, a strong and simple one can be tested quickly. But a result that approaches confidence without quite becoming certainty creates a different kind of tension, because it resists both dismissal and acceptance. That is where K218b now lingers. The possible signs in its atmosphere do not sit in the comfortable zone of pure speculation, where imagination can wander freely because evidence is thin, nor do they rest in the calm territory of settled fact, where repeated confirmation closes the case. They occupy the narrow band in between, where the numbers begin to point in one direction, often enough to disturb everyone involved, yet still leave just enough room for caution to survive. In public language, confidence is often treated as if it were a simple measure of truth. A result is either likely or unlikely, strong or weak, certain or uncertain. But the real practice is more delicate. The atmosphere of a distant planet is not read once and declared known. It is reconstructed through layers of observation, instrument calibration, model fitting, and statistical comparison. Every step introduces choices. Each choice has consequences. A feature that looks persuasive under one retrieval model may weaken under another. A signal that seems to rise clearly above noise may become less distinct if the baseline is handled differently, if stellar activity is modelled another way, or if clouds are given more freedom in the fit. Confidence, in this setting, does not mean a direct count of truth. It means the measured preference of one explanation over alternatives within the space of tested assumptions. That is why the confidence attached to the dimethyl sulfide claim matters so much and yet remains so difficult to interpret outside the field. A result described as around 99.7% confidence sounds decisive, almost theatrical in its neatness. It feels as though the atmosphere has already confessed. But in astronomy, such a number is not a final seal. It is a statistical condition that depends on the quality of the data, the model family used to retrieve the atmosphere, and the completeness of the alternatives considered. The signal may be unlikely to arise from random noise under the chosen analysis, yet still remain vulnerable to unknown systematics or incomplete chemistry. In other words, the statistics may say the feature is probably real, while still leaving open what, exactly, the feature represents. This is the core discomfort of the planet. The deeper the data are examined, the more the noise seems insufficient to explain everything. The telescope has not merely glimpsed one errant fluctuation, it has recorded a suite of atmospheric features across repeated study. Water vapour appears plausible. Methane and carbon dioxide have supporting structure. The hydrogen-rich nature of the atmosphere fits the larger picture. Against that background, the sulfur-bearing feature begins to feel less like a stray mark and more like part of a coherent retrieval. The confidence does not rest on a single isolated bump in the spectrum. It grows from a chemical portrait that keeps returning, with slight variations, to the same broad world. Yet astronomy is careful for good reason. Many of its great embarrassments begin in statistical enthusiasm. The universe is generous with false order. Detectors drift, stars flicker, pipelines imprint subtle signatures. Background noise forms shapes that resemble meaning when the sample is small and the desire to find structure is large. Researchers working with exoplanet atmospheres know this more than most, because they often operate near the edge of what instruments can do. They are asking faint changes in starlight to reveal gases on worlds that cannot be directly resolved. It is less like reading a sentence and more like inferring the existence of a library from the weight of air in a sealed room. Precision is possible, but humility must remain close. So the statistical argument becomes less a declaration and more a controlled struggle against self-deception. One analysis is not enough. Different teams revisit the same data. Instrument systematics are re-examined. The star itself becomes part of the problem, because red dwarfs are not featureless lamps. Their surfaces can contain spots, faculae, and temperature contrasts that alter the apparent transmission spectrum of a planet passing across them. If the star's own light varies subtly with wavelength, then the atmosphere of the planet can inherit phantom features. A retrieval that neglects stellar complexity may overstate atmospheric confidence. Thus, the statistics of K218b are never only about the planet. They're also about how well the star has been understood, how carefully the instrument has been characterized, and how completely the modeling has explored ambiguity. But it is precisely because these tests are severe that the continued survival of the anomaly feels so unsettling. If the feature had vanished early under stricter treatment, the story would have ended quietly. If repeated reanalysis had flattened the case into ordinary uncertainty, the planet would still be interesting, but not haunted by the same possibility. Instead, the atmosphere remains difficult in a more durable way. The retrievals do not collapse into emptiness. The chemistry still seems active. The sulfur signal, though tentative and debated, does not dissolve into obvious error. The confidence is not static, either. It can shift with methods, with assumptions, with future observations. But even shifting confidence has meaning when it keeps circling the same improbable idea. There is a deeper lesson in that. Statistics do not remove mystery, they refine it. Before the telescope observes the planet in detail, the mystery is broad and nearly useless. Could life exist there? Could the atmosphere be unusual? Could the world hold water? Such questions are too wide to grip. After the data arrive, the questions become narrow enough to trouble the mind properly. If a sulfur-bearing feature is really present, how much of it is there? What pressure level in the atmosphere contributes most strongly to the signal? Could unknown abiotic chemistry produce it under hydrogen-rich conditions? How much do clouds mute the spectrum? What level of stellar contamination remains plausible? The mystery does not shrink in emotional force, it sharpens. That sharpening is one reason terms like 3 sigma gain such cultural power in astronomy. They sound like thresholds, and in some practical sense they are. A detection at roughly that level means the signal is unlikely to be a mere accident under the tested model, but such thresholds are conventions, not magical transformations of data into certainty. In particle physics, a stronger threshold is often demanded before declaring discovery. In astronomy, especially in frontier observations, the interpretation can be even more delicate because the universe itself is not a controlled laboratory. Every planet is its own experiment. Every atmosphere carries conditions not easily reproduced in full. The significance level may therefore tell only part of the story. A statistically strong feature in an incompletely understood system can still hide a conceptual trap, and yet it is impossible to miss what the numbers are doing psychologically. They pull the planet closer. They make caution feel less like discipline and more like resistance. If the confidence were only moderate, the imagination would remain loosely attached. If it were overwhelming, the discipline of science would simply accept the burden of proof and move forward. But the present state is more dangerous to thought. It invites almost belief. It places the researchers themselves in a peculiar posture, where they must keep repeating that no definitive claim has been made, while also knowing that the atmosphere is no longer behaving like an ordinary blank candidate. The numbers do not grant permission to declare life. They do something subtler and perhaps more destabilizing. They make the hypothesis feel persistent. This persistence matters because atmospheres are cumulative systems. A possible biosignature on K218b does not emerge from a silent backdrop. It sits within a context of plausible water, methane, carbon dioxide, and hydrogen, around a world that may be temperate enough for liquid water and stable enough for long chemical evolution. Each of those elements carries its own uncertainty. None is beyond debate in its exact abundance or interpretation, but together they form a probability landscape, and within that landscape the sulfur feature gains leverage. Statistics in such a case become relational. It is not only whether one molecule is favoured over noise, it is whether a whole atmospheric scenario continues to hold together when stress is applied. That is why future observations matter so much. Statistics are not frozen. They live and die by repetition. More transits can deepen the signal or wash it out. Different instruments can test nearby wavelengths and improve molecular discrimination. Better stellar models can either reduce the atmospheric case or clean it. Higher signal-to-noise observations may show that the suspected sulfur feature is truly there, or that a different molecule has been hiding behind it. The confidence in any one explanation can rise, fall, or split into alternatives, but even this dependence on future work has become part of the unease, because the planet has already advanced beyond the point where more data are merely desirable. More data now feel necessary, as though the world has asked a question, and the instruments are morally obliged to answer. There is also the unsettling fact that even a weaker biosignature claim would not restore comfort. Suppose future analyses reduce the confidence in dimethyl sulfide specifically. The atmosphere would still remain unusual. The possibility of a warm ocean world under hydrogen would still stand as one of the more provocative planetary scenarios yet studied. The chemistry would still require explanation. The same data that tempt biology also challenge standard expectations for what a habitable environment should look like. In that sense, statistics do not govern whether K218b is interesting. They govern only which version of the mystery becomes dominant. Stronger evidence points toward biosignature. Weaker evidence points toward unfamiliar planetary chemistry. Both directions lead away from simplicity. So the numbers continue to hover over the world like a second atmosphere, thin but influential. They are not the planet itself. They are not the ocean below, if an ocean exists, nor the possible metabolisms that might inhabit it. They are the mathematics of human restraint, the formal language by which suspicion is allowed to harden without becoming dogma. Around 99.7% is not a finish line. It is a narrow ridge between fantasy and fact, and K218b remains balanced there with unnerving steadiness. The signal is too coherent to dismiss lightly, too model-dependent to embrace carelessly, and too suggestive to leave emotionally untouched. In that unstable balance, the statistics do not calm the mystery. They make it harder to escape. If the atmosphere of K218b is the first visible clue, the ocean beneath it is the hidden engine that gives those clues meaning. Nothing in the telescope data shows waves, currents, coastlines, or a surface broken by storms. No camera has ever seen the top of its sea. Yet the planet keeps drawing thought downward. A hydrogen-rich atmosphere, signs of water vapor, a size larger than Earth, but smaller than the giant outer planets, and temperatures that may allow liquid water together encourage one broad possibility again and again. Beneath the clouded sky may lie a vast global ocean, not shallow like Earth's seas spread over rock, but deep on a scale that weakens ordinary language. The world may not have a surface in the familiar sense at all. It may have an upper atmosphere, then cloud and mist, then warm water descending through pressure into a realm where ocean becomes something almost geological. That idea begins as a model, not a sighting. Planetary scientists do not infer oceans carelessly, because water is too useful a solution and too easy a fantasy. But K218b does not fit neatly into the categories that once shaped the search for habitability. It is too large to be treated simply as a rocky planet with a thin, breathable shell. At the same time, it may be too modest in size and density to belong among the classical gas giants. Between those extremes lies a world that may contain a large fraction of volatile material, especially water, with a hydrogen-rich atmosphere draped above it. If that picture is even partly correct, then this is not merely a planet with water. It is a planet defined by water. The consequences of that are harder to absorb than the word ocean first suggests. On Earth, oceans are deep enough to humble imagination, yet they remain a thin film compared with the size of the planet. Beneath them lies crust, mantle, and the slow exchange between geology and sea that helps regulate climate across immense spans of time. K218b may be arranged differently. Its water layer could be vastly deeper, perhaps so deep that the lower regions pass into high-pressure forms unfamiliar to ordinary experience. In such conditions, water does not always remain the liquid known in rivers and rain. Under enough pressure, it can enter exotic states, compressed into structures more like mineral phases than fluid seas. Between the upper ocean and any deeper interior, there may exist transitions that isolate one layer from another, or perhaps unstable boundaries that still allow exchange. No one knows which picture is right, but the uncertainty itself is revealing. This is not a sea resting on land. It may be a world where water becomes the main architecture. That possibility creates both hope and difficulty for life. Water is the most generous solvent known to biology on Earth. It allows molecules to meet, dissolve, separate, and recombine. It moderates temperature. It carries nutrients and waste. It invites complexity because it supports motion without demanding stability and form. A vast ocean would therefore seem, at first, to be good news. More water means more room for chemistry, more volume for ecosystems, more time for gradients to form and persist. Yet too much water may also create a problem. If the ocean is so deep that it seals itself off from the mineral interior, then one of the great engines of Earth's long-term habitability may be weakened. On Earth, rock and water interact constantly. Minerals dissolve. Carbon cycles through sea and stone. Volcanic outgassing replenishes atmospheric ingredients. Tectonics and weathering slowly regulate climate. A world of almost nothing but water might lose some of that steady exchange. The ocean could become chemically rich near the top but isolated below, or stable in ways that reduce the tension life often feeds upon. Still, K218b may not obey the most limiting version of that picture. Internal heat from its formation, residual radioactivity, or slow gravitational compression may keep the deeper layers dynamic. Convection in the ocean could transport dissolved material upward and downward over immense timescales. A thick hydrogen atmosphere may also change the chemistry of the surface ocean, loading it with gases and creating energy-rich gradients not common on Earth. This is where the world becomes more speculative, but also more intriguing in a hydrogen-rich environment. Life would not need to imitate Earth's modern oxygen-based metabolism to matter at planetary scale. It could draw energy from reactions between hydrogen, carbon compounds, sulfur chemistry, and dissolved substances cycling through sea and air. A biosphere on such a planet might not be built around sunlight alone, or even around the surface in the ordinary sense. It could inhabit boundary layers where the ocean meets the atmosphere, where dissolved gases enter water, or where warmth and chemistry create continuously replenished imbalances. That is one reason the possible sulfur signal in the atmosphere feels so tied to the image of an ocean below. On Earth, dimethyl sulfide is strongly linked to marine microbial life. The association does not prove the same mechanism elsewhere, but it exerts a gravitational pull on thought. If K218b is a water world, and if a sulfur-bearing molecule resembling dimethyl sulfide is present in its atmosphere, then the simplest speculative bridge between these facts leads through an oceanic biosphere. Not forests, not animals, not visible continents, but microbial or plankton-like life in huge numbers, drifting or swimming or suspended through warm upper waters, altering dissolved chemistry, releasing volatile compounds, and slowly feeding those compounds into the sky. The atmosphere in that picture becomes not a shell above the sea but an extension of it. What rises from the water leaves a trace in the light years away. The temperature estimate sharpens that image. A world hovering in a warm regime around 120 degrees Fahrenheit is not comfortable by human standards, but it is not beyond life's known capacity. On Earth, organisms endure and even thrive in waters hotter than that, particularly in deep marine environments and geothermal systems. Warm water accelerates chemistry. Reactions proceed more quickly. Molecules move more freely. The cost is that some structures become less stable, but life often solves such problems with adapted chemistry. If K218b maintains a stable warm ocean over long spans of time, then the sea may be less a marginal refuge than a giant reactor, one tuned not to one narrow ecosystem, but to world-scale persistence. Life there, if it exists, may not struggle against its ocean. It may flourish because the ocean remains warm, deep, and chemically restless everywhere at once. The pressure within such a sea is harder to imagine. Even the upper ocean, beneath a thick hydrogen atmosphere and stronger gravity than Earth's, could sit under conditions foreign to terrestrial biology. That does not make life impossible. It only means that any living systems present would be built for a physical world unlike this one. Cells, membranes, enzymes, and metabolic pathways would need to function under different balances of pressure, dissolved gas content, acidity, and temperature. If Earth's biology offers any lesson, it is not that life demands one exact condition, but that once chemistry crosses a certain threshold into self-maintaining complexity, adaptation follows wherever energy and matter continue to flow. The ocean of K218b, if real, offers no obvious shortage of matter. The question is whether it offers the right kinds of energy gradients for biology to seize and elaborate. Some of those gradients may arise from light. A red dwarf star provides a different spectrum than the Sun, weighted more heavily toward the red and infrared part of the range. If the upper atmosphere and cloud cover allow enough of that light to penetrate, the upper ocean might support photochemistry unlike anything dominant on Earth today. Other gradients may arise from chemistry alone, especially if the sea is loaded with hydrogen, methane-related compounds, carbon dioxide, and sulfur species. On Earth, entire ecosystems survive without sunlight, using chemical disequilibrium as their energy source. They inhabit dark vents, buried sediments, and anoxic waters. K218b may extend that logic across a whole planet. It may be a world where chemistry itself supplies much of the living tension. Yet one uncertainty continues to darken the picture in a productive way. No one knows where the ocean ends. If it extends downward too far into high-pressure phases, the deeper regions may become inaccessible to the upper biosphere. A living layer might exist only near the top, above the crushing transitions below. Alternatively, internal heating and mixing might keep a larger fraction of the water column active than current models assume. The ocean could be stratified into habitats, each with distinct chemistry, each feeding subtly into the atmospheric whole. A sulfur-bearing gas detected from afar might therefore be the signature not of one uniform biosphere, but of stacked ecosystems hidden in pressure and darkness, communicating only through slow flux and planetary circulation. The world remains unreadable in detail, but the unreadability now has structure. There is also a philosophical unease in a planet so dominated by ocean. Earth teaches the human mind to associate significance with surfaces, with land, with edges where one thing meets another visibly. K218b may deny all of that. Its most important activity may occur under cloud and pressure, far below any horizon, in waters that never break against shore, because there may be no shore to break against. Life there, if present, would not announce itself through monuments or continents or seasonal colours. It would announce itself chemically, by leaning on the atmosphere until a telescope notices. That is perhaps the strangest possibility of all. A world can be alive and still remain visually hidden, turning its sky into the only biography available to distant observers. So the image of the ocean persists, not because it is proven, but because it helps explain why the atmosphere of K218b feels less like a passive envelope and more like the exposed surface of a deeper system. Beneath the hydrogen sky may lie a warm sea that has lasted long enough for chemistry to organize itself beyond chance. Beneath that sea may lie layers of pressure, ice, or fluid complexity that no present instrument can map. Somewhere in that hidden vertical world, matter may be cycling, reacting, and perhaps reproducing on scales large enough to alter the air. The telescope cannot see the ocean. It sees only what the ocean, if it exists, may be breathing upward. The star at the centre of this system does not command attention in the way the Sun would if seen from far away. It is smaller, cooler, dimmer, and at first glance less grand. In the long hierarchy of stars, red dwarfs seem modest, almost reluctant sources of light, burning with a steadiness that can make brighter stars look wasteful by comparison. Yet the modesty is deceptive. A red dwarf is not merely a lesser sun, it is a different kind of timekeeper. It consumes its fuel so slowly that the lifespan of such a star can stretch far beyond the current age of the universe. Around that kind of star, chemistry is given not only a place but an almost unreasonable amount of time. If life requires patience, then a quiet red dwarf may be one of the most patient environments the cosmos can offer. That is one reason K218b refuses to be treated as a temporary curiosity. The planet does not circle a massive star racing toward exhaustion. It moves around a red dwarf that may continue shining for spans so long that ordinary human history becomes too small even as metaphor. Earth has had roughly 4 billion years for life to move from simple chemistry to microbial persistence, then to complex cells, multicellular organisms, and eventually the brief surface layer of intelligence now studying other worlds. Around a long-lived red dwarf, a planet with stable conditions may be granted far more than that. It may be given repeated chances, failed starts, evolutionary detours, and long eras of quiet continuity. If a world around such a star enters habitability early and remains there, then biology need not rush, it can deepen. This possibility changes the emotional scale of the K218 system. A warm ocean world around a red dwarf is not simply habitable in the narrow sense of allowing liquid water now. It may be habitable in time-rich terms, a place where the same broad environmental conditions persist long enough for rare chemistry to become ordinary biology, and for ordinary biology to become ecologically dominant. That does not prove anything about the present world, but it changes what seems plausible. On Earth, life appears quickly once conditions allow it, at least in microbial form. Complexity takes longer. Atmospheric transformation takes longer still. A red dwarf offers something extraordinary to such processes. It offers duration without drama, a source of energy so restrained that evolution may unfold in a climate of persistence rather than interruption. Yet red dwarfs also bring their own shadow. Many are restless when young. They flare. They release bursts of radiation and particles that can strip atmospheres or alter surface chemistry dramatically, especially on planets that orbit close enough to remain warm. This is the first great objection to habitability around such stars. Because a red dwarf is dimmer than the Sun, the habitable zone lies much closer in. A planet placed there receives enough light for liquid water, but it also endures the star at close range, where magnetic violence can matter more. In the early life of some red dwarfs, this violence may be fierce enough to sterilize surfaces, dissociate water, erode atmospheres, or simply prevent stable conditions from holding long enough for biology to gain a foothold. The question then becomes not whether a red dwarf can support life in principle, but whether a given red dwarf settles down soon enough, and whether its planet can endure the stormy youth. K218 seems important partly because the answer may be yes. The star is not known as one of the most violent examples of its class. It appears comparatively moderate, a word that in stellar terms can still conceal activity, but which matters immensely when the subject is long-term habitability. If the planet retains a substantial hydrogen-rich atmosphere today, then either the star is calm enough now and in the recent past, or the planet's gravity and atmospheric reservoir are strong enough to resist erosion better than smaller rocky worlds might. Perhaps both are true. In that case, the red dwarf does not merely pose a problem to be overcome, it becomes part of the solution. Its long life and reduced luminosity create the conditions for persistent warmth close in, while the planet's own mass helps preserve the atmosphere that smooths climate and protects deeper layers. The proximity of the planet to its star introduces another complication that slowly turns into another possibility. K2-18b likely keeps one face turned toward the star at all times. Tidal locking is the natural consequence of close orbits over long spans. One hemisphere remains in perpetual day, the other remains in perpetual night. At first, this seems hostile to continuity, as if the world must be split between extremes. But on a planet with a thick atmosphere and perhaps a global ocean, this arrangement may produce not catastrophe but circulation. Heat is carried from the lit side toward darkness. Winds move, clouds form and reform. Ocean currents, if present, may redistribute energy below. Instead of seasonal oscillation like Earth's, the world may settle into a stable geometry of climate zones tied to a fixed star position. The day side need not burn. The night side need not freeze. The entire planet may live inside a permanent pattern that biology can learn and exploit. There is something quietly unsettling in that idea. Earth's biosphere is shaped by cycles that change with day, night, season, axial tilt, and the shifting balance of light. K2-18b may live by different rhythms. Its star hangs in one place over one hemisphere forever. Twilight, if it exists as a broad transitional zone, may remain fixed. The dark side never waits for dawn. Life evolving under such conditions would not simply adapt to the environment. It would internalize an entirely different planetary logic. Migration, dormancy, metabolism, and ecological structure might all organize around a geography of permanence. If biology exists there, it may not think in seasons at all. It may think, in its own non-conscious way, in gradients of pressure, light, and circulation that do not move across the globe but remain anchored over geological time. The red dwarf also changes the quality of light itself. The star emits a larger share of its energy at red and infrared wavelengths than the sun does. That matters for climate because different atmospheres absorb and redistribute such energy differently. It also matters for any hypothetical photosynthetic or light-using biology. On Earth, the visible spectrum is not merely scenery, it is part of metabolism. Pigments evolve to harvest the wavelengths most available and useful in local conditions. Around a red dwarf, those conditions shift. If life in the upper ocean or atmospheric boundary of K2-18b uses light, it may be tuned to a different color regime altogether, one shaped by deep red illumination filtered through hydrogen-rich clouds. The world may glow in an optical logic unfamiliar to Earth, not because it is fantastical, but because its star teaches chemistry to work with another spectral emphasis. And still, the deeper importance of the star is time. The scale of red dwarf longevity introduces a thought that becomes harder to ignore the longer the planet remains under scrutiny. If K2-18b becomes clement early and stays clement long, then any biosphere there may not merely be active. It may be ancient in a way Earth's is ancient, but stretched. Even if life arises only after long delays, the opportunity remains open. Even if mass extinctions occur, the star continues. Even if atmospheric conditions fluctuate, the broad energy source persists with almost unreasonable patience. A world like this does not need to get everything right quickly. It has ages to experiment. That is what makes the possible sulfur signal feel so charged. It does not belong to a world with a short and fragile window. It belongs to a system where chemistry may have had almost too much time to become something more. This also widens the implications beyond a single planet. Red dwarfs are the most common kind of star in the galaxy. They vastly outnumber stars like the Sun. If even a small fraction of their planets can retain atmospheres, preserve water, and settle into long-term stability after youthful turbulence, then the number of potentially life-bearing worlds rises dramatically. The old search for Earth twins begins to look narrow, perhaps too narrow by an order of magnitude hard to accept emotionally. Most life in the galaxy, if it exists, may not circle stars like the Sun at all. It may spend its ages under dimmer skies, in tidally locked climates, above warm oceans, inside atmospheres rich in gases unfamiliar to human lungs. K218b therefore matters not only because of its own mystery, but because it may be a representative of a much larger hidden category. That possibility intensifies rather than resolves uncertainty. If red dwarf systems can host living worlds, then their long lifetimes raise new questions. Does extreme longevity encourage complexity? Or does it trap worlds in stable microbial states for ages beyond imagining? Do tidal climates simplify ecology or create more durable niches? Does stellar flare history sterilize more planets than it spares? Or do thick atmospheres and oceans shield enough of them to let life persist below? K218b becomes one place where these larger questions begin to gather. Its atmosphere is not only a local puzzle, it is a test of whether red dwarf habitability is a fringe exception or a major mode of life in the galaxy. The star's modest appearance makes all of this feel even stranger. Great discoveries are often expected to come from dramatic places, from brilliant stars, violent phenomena, or planets immediately recognizable as cousins to Earth. Instead, the system offers a dim red point in Leo and a world hidden by cloud and spectrum, where the most important evidence arrives as missing light and possible sulfur chemistry. The red dwarf does not overwhelm the scene. It allows it. Its power lies not in brightness, but in endurance. It is a small furnace that refuses to go out, and that refusal may be enough to let a planet breathe for spans longer than human thought is comfortable holding. So the star remains there behind the mystery, quietly shaping everything. It keeps the planet close, locks its rotation, softens its light, stretches its seasons into fixed geography, and extends the calendar of possible biology almost beyond meaning. If K218b is alive, then the red dwarf is not merely its sun. It is the reason life may have had time to become atmospheric, persistent, and detectable. And if the world is not alive, then the star still forces a larger conclusion. It shows that the galaxy is filled with long-lived laboratories in which chemistry can work slowly, repeatedly, and under conditions once dismissed as secondary. Either way, the red dwarf makes the planet harder to ignore. It turns one strange atmosphere into a hint about the broader architecture of living possibility in the Milky Way. Long before the atmosphere of K218b becomes a question about life, it is first a question about whether any instrument built by human hands can even hear a world so faint. The James Webb Space Telescope is often described as the most powerful observatory ever sent into space. But power in this case is not force, it is restraint. It is the ability to remain cold, still, and precise enough that a tiny change in distant starlight can be separated from the far greater brightness surrounding it. Everything about the telescope is arranged around that discipline. Its great segmented mirror does not exist to produce grand images alone. Its deeper purpose is to gather enough ancient light that chemistry on remote planets can begin to leave marks strong enough to study. K218b becomes one of the first worlds to test how far that purpose can be taken before the edge of detection begins to blur into interpretation. The telescope lives far from Earth, not in the low orbit that made the Hubble Space Telescope famous, but much farther out, near the gravitational balance point called Lagrange 2. There it travels with Earth around the Sun while keeping the Sun, Earth, and Moon on the same side of its enormous layered sun shield. That shield is one of the quiet marvels of the observatory. It blocks heat and light so effectively that the instruments on the shadowed side can cool to temperatures where infrared radiation from distant worlds becomes measurable. Without that cold, the telescope would be blinded not by the cosmos but by its own warmth. It would glow too brightly in the very wavelengths it is meant to observe. So the first condition for seeing the possible breadth of another world is not magnification or image sharpness. It is silence from the machine itself. That silence has to be maintained with extraordinary care. The mirror, composed of gold-coated segments, must behave as though it were one nearly perfect surface. Its alignment is not simply a triumph of engineering, but a prerequisite for trust. If the mirror drifts or deforms beyond the tiny tolerances built into its operation, the light gathered from a star and its transiting planet begins to smear, and smearing at this level is not aesthetic damage, it is lost information. The atmosphere of K218b exists in the data as minute differences in brightness across wavelength, differences so small that a subtle instrumental instability could imitate them or erase them. The telescope therefore does not merely observe, it holds itself together against the temptation to blur the truth. Even then, the instrument is not neutral in the easy sense. Every detector has habits. Pixels respond slightly differently. Readout patterns leave signatures. Thermal changes, however controlled, can shift baselines. Tiny pointing motions can move light across the detector in ways that masquerade as wavelength-dependent behavior. The science of exoplanet atmospheres through transit spectroscopy is therefore not just astronomy. It is a continuing contest between signal and systematic error, between a real planetary feature and the subtle fingerprints of the machine trying to reveal it. The James Webb Space Telescope succeeds not because it avoids this contest, but because it permits the contest to be waged at all. It gives astronomers enough quality in the data that instrumental doubt can be modelled, challenged, and in many cases reduced to something smaller than the planetary story. For K218b, this matters especially because the world is not directly resolved as a separate disk. The telescope is not photographing an ocean under an alien sky. It is collecting the combined light of star and transit, then extracting from that event the fractional imprint of the atmosphere. The planet is effectively hidden inside its effect. That is why the telescope begins to feel less like a window and more like an interrogator of light. It does not behold worlds. It compels photons to surrender the history of their passage. Some have crossed the clear upper regions of the atmosphere. Some have been blocked by clouds. Some carry the absorption pattern of methane. Some of water. Some perhaps of a sulfur-bearing molecule that should not be casually present on a distant temperate world. The telescope listens to all of them at once and then forces them into order. Its instruments make that possible by splitting light into spectra with enough detail to reveal molecular behavior. Different observing modes offer different pieces of the atmospheric puzzle, some better for broad wavelength coverage, some for narrower regions where specific molecules matter. In the case of K218b, this layered approach becomes crucial. No single pass across the star can settle everything. Multiple transits are needed. Different instrument settings test whether the same broad atmospheric story keeps returning. This repetition is where the observatory begins to feel almost patient in a human sense. It waits for the planet to cross the star again, gathers another thin strip of altered light, and compares it to what came before. The world is never seen all at once. It is assembled from recurring acts of disappearance. There is an irony in that method. The more important the question becomes, the less dramatic the raw data appear. Public imagination wants discovery to arrive in a blazing image, but the telescope's most unsettling findings often emerge from curves, not pictures. A line of brightness dipping during transit, a spectral feature slightly deeper here than there, a retrieval model fitting one molecular combination better than another. K218b is a perfect example of this inversion. One of the most provocative worlds yet examined is known not through landscape but through subtraction, through the discipline of noticing that a tiny fraction of starlight fails to arrive in the expected way. The telescope does not bring the world nearer by making it visible in ordinary terms. It brings it nearer by making it chemically legible. That legibility remains partial, and the partial nature of it is what gives the observatory its almost eerie authority. The James Webb Space Telescope can say something about gases high in the atmosphere. It can constrain temperature structure in a broad way. It can indicate whether clouds are likely present, whether the atmosphere is extended, whether certain molecules fit better than others. But it cannot simply state what lies beneath the clouds, or whether an ocean truly spans the planet, or whether the possible biosignature candidate is produced by living systems, unknown chemistry, or an overlap in molecular interpretation not yet fully resolved. The instrument reaches far enough to make the question sharper, not far enough to close it. In that sense, its greatest strength is also the source of the lingering unease. It can reveal too much to ignore and too little to rest. There is also the matter of scale, which changes the emotional meaning of the telescope itself. The light gathered from K218b has crossed more than a century of space-time before touching the mirror. Whatever chemistry shapes that atmosphere does so in a past that has already slipped away. The observatory is therefore not only sensing a distant planet, it is sensing a historical state of that planet. The possible sulfur signal, if real, belongs to a world as it existed when Earth still lived in an earlier technological age. This makes the telescope feel less like a machine aimed outward than a device that bends time into evidence. It receives old light and turns it into a present tension. It lets a planet from another era interfere with human certainty now. Perhaps that is why the observatory's role in this story becomes larger than the engineering. It begins to resemble a threshold machine. One built not to answer old questions decisively, but to create a new class of difficult questions humanity has never had to live with before. Before a telescope of this capability exists, the search for life beyond Earth remains largely inferential and often speculative. Worlds can be counted, sizes and orbits can be measured, habitability can be discussed in broad terms. With the James Webb Space Telescope, atmospheres become available to direct chemical scrutiny. The search changes from where life might exist to what traces a living or almost living world might already be leaving in the light. K218b is one of the first major tests of that transition, and it arrives not as closure but as strain. The instrument has opened the door just far enough to reveal that the corridor beyond is crowded with ambiguous signs. That ambiguity is not failure. It is the shape of first contact with complexity. When new instruments first enter their mature scientific life, they rarely produce only clean answers. More often they reveal how much earlier science has simplified for lack of reach. The James Webb Space Telescope is doing exactly that. It is not merely confirming what astronomers already expected to find. It is exposing worlds that sit between categories, atmospheres that refuse easy modelling, and possible chemical combinations that force old assumptions about habitability to widen. K218b matters because the telescope can see enough of it to make it troublesome. A lesser observatory might have left the world in the safer category of broad interest. This one presses it into the category of atmospheric discomfort. The machine itself therefore becomes part of the mystery. Not because it behaves strangely, but because it changes the scale of what counts as a meaningful anomaly. Before, a remote ocean world around a red dwarf star might have been little more than an entry in a catalogue. Now its atmospheric chemistry can disturb debates across astronomy, planetary science, and the broader public imagination. The telescope has not made the universe simpler, it has made it intimate. It has allowed the thin outer air of a distant planet to become a subject of serious argument. That is an astonishing shift, and perhaps an irreversible one. Once an observatory can plausibly detect a biosignature candidate on a world more than 100 light-years away, every similar planet becomes charged differently. Every transit begins to carry the possibility that another atmosphere may contain a puzzle of the same kind. So the James Webb Space Telescope remains there in its cold station beyond Earth, its mirror open to the dark, its instruments tuned to tiny losses of light, continuing the slow work of turning alien skies into spectral evidence. It does not promise certainty. It offers something more difficult and perhaps more consequential. It offers access. Through that access, K218b stops being a remote object and becomes a chemically legible place, one whose air may be carrying the trace of processes deep below. The telescope cannot see the organisms, if there are organisms. It cannot descend through the clouds or touch the sea, but it can do something that once seemed almost as unlikely. It can look across interstellar distance, measure the atmosphere of a hidden world, and find in that atmosphere enough strangeness to make the silence of space feel less empty than before. Once a single planet begins to look difficult in the right way, the larger sky changes with it. K218b does not remain isolated for long in the mind, even if the data themselves remain specific to one world. The moment a hydrogen-rich ocean planet around a red dwarf star shows atmospheric chemistry that resists easy dismissal, every catalogue of nearby worlds quietly changes character. Planets that once seemed merely odd now begin to look unfinished, not because the science has failed to describe them, but because the categories used to judge them may have been too narrow from the beginning. One world with a troubling atmosphere can be treated as an exception. Several worlds with overlapping forms of promise begin to suggest a pattern, and patterns, once suspected, are harder to contain than any single discovery. For years, the search for life beyond Earth is guided by a strong preference for familiarity. Small rocky planets matter most. Sun-like stars feel safest. A certain range of temperature and surface pressure is treated not merely as one possibility among many, but as the central stage on which biology is expected to appear. This approach is understandable. Earth is the only living world known with certainty, and every serious search begins with the only example available. But examples can imprison thought as easily as they guide it. The exoplanet census has already shown that the galaxy is not built around the layout of the solar system. Super-Earths are common, mini-Neptunes are common, compact systems around red dwarfs are common, deep-water worlds may be common. The cosmos has been offering architectures that Earth never taught the human imagination to expect. K218b matters because it takes one of those architectures and gives it chemical weight. That weight becomes heavier when placed beside other systems now under scrutiny. Some nearby planets orbit in the habitable zones of red dwarfs and have already become central to future atmospheric study because they are small enough, close enough, and well aligned enough to let their stars illuminate their skies during transit. These worlds differ in size, likely composition, and stellar environment. Yet they share an unsettling implication. The local neighbourhood of stars may contain many planets that do not resemble Earth closely, and yet remain fully capable of preserving atmospheres, water, and long-term energy flow. Some may be rocky and compact, some may be volatile rich, some may sit in climates that alternate between clement and harsh, depending on cloud cover, tidal locking, and stellar activity. The point is not that they all look inhabited. The point is that none can now be dismissed simply for being unlike home. This widening of attention reaches beyond mature planets to younger systems as well. Around some stars, debris disks remain visible. broad rings of dust and ice tracing the unfinished architecture of planetary formation. These rings are not merely decorative halos. They record the dynamical work of worlds taking shape, clearing gaps, shepherding fragments, and reorganizing matter over millions of years. The sample that gave rise to this script points towards such systems as part of the same unfolding mystery. A young star encircled by rings, a gap cut through debris, a planet inferred not first from a transit but from the absence of material in its orbital path. That kind of discovery matters for more than planetary census. It reminds the search for life that habitable worlds do not appear fully formed and static. They emerge from violent, dusty, unstable beginnings, and some may pass through phases of warmth and atmospheric development long before their systems have settled into old age. The connection between these young systems and K218b is not direct in a narrow observational sense. No one confuses a mature sub-Neptune or ocean world around one red dwarf with a newly formed planet in a debris disk around another star. But the narrative link is real. Both kinds of discovery force astronomy to watch planets as evolving chemical systems rather than as fixed categories. One world is still gathering itself from dust and ice. Another may have spent ages under a dim star, deepening its atmospheric chemistry until a possible sulfur signature reaches a telescope far away. Together they reveal a wider truth. The galaxy is not filled with finished planets waiting passively to be labelled. It is filled with worlds in motion, worlds becoming, worlds retaining heat, losing heat, gaining atmospheres, shedding atmospheres, hiding oceans, opening climates, and perhaps in some cases allowing chemistry to cross into life. That is why the idea of one planet becoming many is not only about counting potentially habitable worlds. It is about learning to see continuity where older astronomy saw separate curiosities. A gap in a debris disk, a warm atmospheric profile, water vapor in a transmission spectrum, methane in disequilibrium, a sulfur-bearing absorption feature hovering near the threshold of significance. Each of these once lives in its own narrow professional subfield. Planet formation studies look at disks, atmospheric studies look at transits, stellar physics looks at red dwarf activity, ocean world modelling considers interior structures and high-pressure water layers. Biosignature work asks which molecules can reasonably point toward life. Now these strands begin to knot together. K218b sits at one knot, but not the only one. The more astronomy learns, the less separate its questions become. This produces a new kind of cosmic map, one not drawn only by distance and orbit but by possibility. Some nearby worlds now matter because their atmospheres may soon be measurable with greater depth. Others matter because their stars are quiet enough to preserve long-term habitability. Others matter because their masses place them in the uncertain range between rocky planets and gas-rich mini-worlds, where new forms of environment may exist. Still others matter because they are young enough to reveal how volatile inventories, debris transport, and early atmospheric chemistry are assembled. The map becomes less about selecting the single most Earth-like destination and more about tracing a continuum of life, permitting conditions across many kinds of planetary systems. In that broader view, K218b is less a lonely wonder than an early landmark. Yet the more the map expands, the more a strange emotional reversal takes place. At first, abundance would seem to reduce mystery. If there are many candidate worlds, then no single one bears too much meaning. But in practice, the opposite happens. A crowded field does not calm the imagination. It makes the silence of certainty more intense. If several nearby systems offer conditions that once seemed improbable and now appear common, then the old assumption of rarity begins to thin out. Life is still unconfirmed beyond Earth in any definitive way. but the environments in which life could plausibly arise are no longer scattered fantasies. They are becoming a population, and once possibility becomes a population, the distance between possible and actual begins to feel smaller than before, even if the scientific burden of proof remains just as strict. The stars themselves reinforce that change. Red dwarfs dominate the galaxy. Around many of them, compact planetary systems appear to be common. Some worlds orbit so close that their years last only days or weeks. Some may be stripped and barren. Some may be cloud-wrapped and hostile. Some may hold on to thick atmospheres and deep reservoirs of water. The emerging lesson is not that every red dwarf planet is a living world. It is that the galaxy has performed far more experiments in planetary climate and chemistry than earlier generations could seriously observe. Earth is not the template the universe keeps copying with minor variations. It may be only one local answer among countless others. K218b becomes important because it hints that one of those other answers may be legible. Even the technologies planned for the near future begin to gather around this possibility. Larger ground-based telescopes are being built with mirrors vast enough to examine exoplanet atmospheres in greater detail from the surface of Earth, especially when paired with adaptive optics that correct for the blur of the atmosphere above. Future space observatories are being discussed specifically to image and characterize temperate planets directly, to seek oxygen, methane, water, and other biosignature combinations around nearby stars. But even before those future instruments arrive, the present generation of observations is already transforming the psychological terrain. K218b has shown that the atmosphere of a remote and strange world can become an object of live scientific dispute in terms that reach beyond specialists. This is what a field looks like just before it becomes crowded with cases that can no longer be treated as isolated. Still, caution remains essential because abundance of candidates is not abundance of confirmation. Many promising worlds will disappoint. Some will turn out to be more hostile than early models suggest. Some atmospheres will prove too cloudy to decode well. Some potential biosignatures will collapse into geology or photochemistry once the data improve. Some planets will remain maddeningly ambiguous for decades. Trapped between model families no existing instrument can fully discriminate. But even disappointment will now work differently than it once did. A negative result on one planet does not restore the older comfort of scarcity. It simply redistributes attention across a field of alternatives. The larger story no longer depends on one perfect Earth twin waiting in a short list. It depends on a growing recognition that the galaxy contains many worlds where chemistry has been given room to become complicated. That may be the quiet revolution hidden beneath the specific drama of K218b. The planet invites the imagination with a possible biosignature. But the deeper shift lies in what that invitation does to the rest of astronomy. It teaches the field to ask broader questions, not only where liquid water might exist, but what kinds of atmospheres can sustain it. Not only whether planets are rocky, but whether oceans, gases, and pressure can create biospheres in settings once ignored. Not only whether stars like the Sun are special, but whether dimmer, older, more common stars may host the larger share of life. A single difficult spectrum becomes a lever. It moves not the planet, but the framework around it. So one world becomes many, not because the evidence on K218b is duplicated everywhere, but because its existence changes the threshold for significance elsewhere. Every future transit of a temperate planet across a small star now carries a sharper charge. Every unusual atmospheric retrieval must be weighed against the possibility that the universe is not merely chemically inventive, but biologically active in more than one planetary style. The debris disks of young stars, the warm atmospheres of mature worlds, the hidden oceans under hydrogen skies, the long patience of red dwarfs, the sulfur-bearing lines in fragile spectra, none of these are proof by themselves. Together they form a new background against which future signals will be read. And in that background, K218b no longer stands alone in the dark. It stands at the beginning of a crowd that has not yet fully come into view. By the time the evidence from K218b gathers into a recognizable shape, the planet has already changed what counts as an open question. It no longer sits in the old category of remote possibility, where life elsewhere belongs only to theory and hope. Nor does it cross into the safer category of certainty, where repetition and consensus turn a bold claim into ordinary knowledge. Instead, it occupies a more difficult threshold, one that modern astronomy is only now learning how to inhabit. The atmosphere appears active. The world appears water-rich, or at least water-linked. The temperatures may permit liquid oceans. The host star offers long spans of stability. A sulfur-bearing feature may be present where biology on Earth leaves one of its most suggestive signatures. None of these facts alone compels a final verdict. Together they create a world that refuses to return to silence. That refusal is what makes the final stage of the story so strange. Human expectation has been trained for discovery as a singular moment. A signal arrives, a photograph is taken, a statement is made. History divides into before and after, but K218b does not grant that shape to the event. It gives instead a slow accumulation of pressure. Each observation narrows the range of innocence. Each analysis removes one comfortable explanation and leaves a smaller, sharper uncertainty behind. The planet does not announce life. It corners thought with the possibility of life until evasion begins to feel less honest than caution. This is not the end of a search. It is the beginning of a new discipline of waiting, where the evidence is already intimate enough to disturb and not yet complete enough to settle. Future observations stand at the center of that waiting. More transits will have to be recorded. More wavelengths will have to be tested. The atmospheric models will have to be stressed until they either fail or harden. Stellar contamination must be constrained with greater confidence. The role of clouds, hazes, and pressure structure must be refined. The sulfur-bearing feature must either separate itself more clearly from nearby alternatives or retreat into the ambiguity from which it first emerged. This is the hard work that follows every serious anomaly. It is not glamorous, but it is where the meaning of the planet now resides. K218b has moved beyond the stage where additional data would simply be interesting. Additional data now decide whether the world becomes a milestone in the history of life detection or a deeper lesson in how exotic atmospheres can mimic the language of biology. Yet even that apparent choice is not simple. Suppose the biosignature case strengthens. Suppose new observations return the same family of features with greater clarity and higher confidence. Suppose the atmosphere continues to prefer a picture in which sulfur chemistry, methane, water, carbon dioxide, and hydrogen coexist in a way that grows steadily harder to explain without a living source. Even then, astronomy will hesitate, because the first claim of life beyond Earth must survive every possible alternative. It must be pressed not only by enthusiasm, but by doubt fierce enough to outlast headlines and fashion. The stronger the case becomes, the more severe the scrutiny will be. A world like K218b may therefore live for years in a state of near confirmation, where the evidence appears overwhelming to the wider imagination, while specialists keep asking what has not yet been excluded. And suppose the opposite. Suppose the sulfur feature weakens under future analysis. Suppose better data reveal a different molecule, a flatter atmosphere, or a more complex stellar effect than first believed. The planet would not return to insignificance. Too much has already changed. It would remain one of the clearest demonstrations that atmospheres on distant temperate worlds can be measured in meaningful chemical detail. It would remain a plausible ocean world around a red dwarf. part of the broader lesson that habitability does not confine itself to Earth-like surfaces under sun-like stars. It would remain a place where chemistry has already widened the imagination of astronomy. Even the collapse of the most provocative interpretation would not erase the transformation. It would only change its form. 218b would become not the first world to hint at life, but the first world to force a more mature language for talking about false positives, ocean planets, and the limits of biosignature confidence. That is why the final threshold around this planet is not really between success and failure. It is between older ways of asking the question and newer ones. For most of human history, the question of life elsewhere is broad, philosophical, and almost impossible to test. Then exoplanets are found, and the question becomes statistical. How many worlds orbit other stars? How many lie in habitable zones? How many resemble Earth in size? With the James Webb Space Telescope and planets like K218b, the question becomes chemical. What is in the air? What should be there if the planet is lifeless? What should not be there if the atmosphere is left to settle? What combination of gases suggests active replenishment? What kind of planet can produce that combination without life? The threshold is therefore not only about one world, it is about the moment astronomy begins to examine other planets, not merely as places but as systems capable of writing their internal processes into the sky. The atmosphere of K218b becomes, in that sense, a form of distant weathered testimony. It is not a message. It is not a deliberate sign. It is the residue of whatever the planet is doing to itself over time, if that residue includes water cycling through a warm ocean, methane rising through a hydrogen-rich envelope, carbon dioxide helping regulate climate, and sulfur compounds leaking upward from processes not easily reduced to rock and light alone. Then the atmosphere is not merely telling observers what the planet contains, it is telling them that the planet remains in motion, that it has not settled into chemical quiet. Worlds that are dead may still be dramatic. They may flare, freeze, vent, and storm. But a world whose atmosphere persistently resists equilibrium invites a different thought. It suggests maintenance. It suggests renewal. It suggests something below the visible layer that keeps the sky from becoming simple. That suggestion becomes even more haunting because of distance. 120 light-years is both vast and intimate in cosmic terms. It is far beyond any journey humanity can presently imagine making in physical form, yet close enough that the planet belongs to the local stellar neighbourhood rather than the deep unreachable background of the galaxy. It is near enough to study, far enough to remain inaccessible, and old enough in the light that reaches Earth to remind observers they are reading history as much as presence. Whatever is happening on K218b has already happened by the time the data arrive. The atmosphere that now disturbs debate belongs to an earlier century of that world. It may still be the same. It may have changed. The telescope cannot know. This lag of light turns the planet into something almost more difficult than a distant object. It turns it into an unresolved past still exerting force on the present. That unresolved quality may be the final reason the mystery deepens instead of resolving. If the world were nearer, the fantasy of future contact would intrude more easily. If it were farther, the signal would feel abstract. At this distance it occupies the perfect scale for intellectual unrest. It can be measured, modelled, debated, and imagined, but not visited, not sampled, not settled by direct inspection. The atmosphere must bear the full burden of interpretation. Everything hinges on the outer air of a hidden planet and on the ability of a telescope in cold darkness to read the chemistry of that air correctly. That is both magnificent and unnerving. It means the first serious approach to extraterrestrial life may come not through contact, radio signals, or visible structures, but through a struggle over spectra, clouds, pressure profiles, and sulfur chemistry in a place no human being will ever see with unaided eyes. And so the planet remains suspended at the edge of declaration. K218b may be a deep, warm ocean world under hydrogen skies, with chemistry vigorous enough to mimic or perhaps sustain a biosphere. It may be the first place where astronomy has come close enough to life beyond Earth to feel its uncertainty physically, as a pressure behind every cautious sentence. Or it may be the world that teaches science how profoundly nature can imitate biology without ever crossing into it. At present, the evidence does not force one ending. It forces only attention. It forces repeated observation, better modelling, broader comparison, and a willingness to stay inside the discomfort of not knowing while knowing more than before. That is the threshold now, not proof, not dismissal, but a narrowing corridor in which each new measurement matters more than the last. The world waits behind its star. The telescope waits in darkness. The atmosphere keeps its pattern for now, and the question remains where it has become hardest to ignore. If the air of K218b is being altered by life, then the universe has already moved beyond solitude in a way that is only beginning to be noticed. If it is not, then the universe has still revealed a world whose chemistry stretches the current limits of planetary understanding. In either case, the final answer has not arrived. What has arrived is stranger. A distant planet has become just clear enough to trouble certainty and just obscure enough to keep the mystery alive.